There we go. All right, so I assume that everybody has viewed the gases video that was actually produced back in February, and then had a chance to look at the review document, the problems there. We're going to have lots of extra time available today since we don't have a lab. So what I thought our order of business would be is for me to do sort of a quick overview of gases, the laws that apply, and not go into a lot of detail, and save the detail for actually working problems. Okay. But I think a framework involving the gas laws might be helpful. And it'll also get my brain in gear too. And then once we get through with that review, then we can go to stay on that same subject and talk about the Boyle's Law lab, so that if you have any questions about that, we'll take those up then. Then after that, we'll go to questions about your upcoming report that's due, in case you have doubts about your first formal report, which most students do. Yeah, okay, so we should have time enough to do all of that today. All right, so gases, Chapter 5. This will be the third exam. And this should be, since the grades are due on the 14th, this should also be included. This grade should be included in your midterm average, along with everything you've done up till now. Let's see. All right, so where to start? I'll leave off discussions of pressures, units of measure. If those come up, you can voice those concerns as we go. But the first law, actually these are roughly in chronological order. The first law that comes up is Boyle's Law. So does anybody remember what two factors are considered? Well, let me just put up all the factors that define the behavior of a gas. Okay, you've got pressure, you've got volume, you've got temperature, and you've got the number of moles. That is the number of particles that are contained, and that's the abbreviation for moles. The one caveat for temperature, it always has to be in Kelvin. Right? So if you are asked a question about a gas at a given temperature and it's in Celsius degrees, you better convert it to Kelvin, which is equal to degrees Celsius plus 273. And we're only going to use 3 significant figures. Your book may make mention of 273.15, but 273 will actually get you closer to the answers that would be on your review and in the test. Okay. Typically, of course, this is going to be in moles. Volume will be in liters, except for special cases, and I'll cover those when we go. And pressure, we're going to consider that in terms of atmospheres. Okay, back to Boyle's Law. So which two of these factors was Boyle's particularly interested in?
Pressure, volume.
I heard volume and pressure. So Boyle's was interested in actually a change in pressure would be the dependent variable. No, excuse me, independent. And pressure would be the, no, that is the dependent variable. This is the independent variable. So what's the difference? The independent variable is the one that the experimenter chooses. So if I choose to change the pressure, then I look at the response, which is the dependent variable. Okay, so when you graph them, generally speaking, you put the independent variable on the x-axis and the dependent variable on the y-axis. So as we change the pressure, what happens to the volume? Okay, so what did Boyle discover? As he increased the pressure, what happened to the volume? Right, it decreased. So it's an inverse relationship. And what he determined was that the response was not linear. Okay? It takes the form of a hyperbola. Okay? He also expressed this in terms of an equation, and he says there's a constant value that applies to pressure times volume. So whenever you have a given pressure times volume, all of the conditions being held constant, when you change the pressure, multiply that times the volume, and you get a constant value. Okay? If you change any conditions, then that constant will change. And those conditions are temperature and number of moles. So you have to have the same amount of gas in the container, and it has to be held at a constant temperature. If those two are constant, then this relationship holds. Okay? So, if I haven't said it before, I'll say it again. Most scientists abhor curves. Whenever we can get them, we take a straight line. Okay? So how do we make a straight line out of this one? Notice here that you have pressure times volume equals a constant. Well, if we take, divide both sides by volume, right, that's valid algebraic procedure, then the volume cancels there and we put on this side. So I'm going to flip this around so that we can put pressure on one side, on the left side, and K over volume on this side. Okay. Now, where am I headed with this? I'm trying to make a straight line out of it, right? So if our model for a straight line is y equals mx plus b, then pressure would correspond to y, and k would be the constant. The slope of a straight line is a constant. Right? So if we factor that out, right, then we have our constant here, and 1 over volume is plotted x. And then, of course, b, what would it be? 0, which means the line should pass through the origin. Okay? So if we plot, in this case, y would be p. There, 1 over v. Then if we plot this line, we get a straight line, and k is the slope. Okay? So you're going to be using that relationship in the Boyle's lab next week. Any questions? Okay. Let's see. I want to be sure I don't want to skip anything. Boyle's. Okay, the next law, gas law, that comes up is Charles' law. Charles was a Frenchman, and he came roughly a century after Boyle's. And what Charles was investigating was the relationship between volume of a gas and its temperature. So in order to investigate these two variables, these two have to be held constant. So the pressure has to be maintained at whatever you choose, but it cannot change. And the number of moles, or the amount of gas contained in the vessel, has to be constant. Then you can investigate how volume responds to temperature. And in that case, the way I just said that, temperature becomes the independent variable, and volume is the response, or the dependent. So volume would be on the y-axis, and temperature would be on the x-axis. So what did Charles discover? Let's see, let me keep track of things that are going on over here. So Boyle's was a constant equals pressure times volume.
Did you ask what Charles was trying to discover?
Yeah, what was the relationship that he found here?
He was trying to see how temperature affects pressure, volume, wasn't it?
Volume, not pressure.
Okay.
Volume. So what did he find? Did the slope go this way or that way? That's the first question.
It went up.
Right, it went this way. And is it a straight line?
Yes.
Right. So that's what Charles discovered. As temperature increases, volume increases. All other things being held constant. So Charles discovered, well, I'll put that here first, that this constant is related to actually, volume is equal to a constant times temperature. So there's your x and there's your y. We could rearrange this and find out that the constant is equal to volume divided by temperature. We just move that over here. Okay. So if we write it that way, we get that expression. But it's just a rearrangement of variables. The point here is that if you multiply two variables times each other and you always get a constant, that will always give you an inverse relationship, a negative slope. Right? Our hyperbola is a negative slope, although the slope continually varies. Right? But this one, the constant is the quotient of two variables. That's always a direct relationship. In other words, as this one goes up, that one has to go up to keep this one constant. Okay. Whereas this condition, in order to be constant, if this one goes up, that one has to go down. Okay. That's the point that I'm trying to make there. So this one's already a straight line. We're perfectly happy just to leave it as is. Now, we're not going to do a Charles law experiment, but there will be Charles law questions in your review document and in the exam. Okay, next. Yes?
For the formula, could you also use V1 T1 equals V2 T2?
Yeah. In fact, I should incorporate that into the discussion. Let's go back to Boyle's and do that one first. Okay? So, all other things being equal, for Boyle's, if pressure times volume is a constant, then if you change the pressure, the volume is going to respond. And whatever new values you get are also going to be equal to that constant. So these were like, this was at one stage of the experiment, and this is at another stage of the experiment. They're both equal to that same constant, right? So the cumulative property says, if this one's equal to that one, and that one's equal to that one, then this one is equal to that one. So that's another way to use, thank you, another way to use Boyle's law is where you have the initial pressure times volume is equal to the final pressure times volume. So if you know, like any equation, if you know three of those, you can find the fourth one. You know this one and this one to begin with, just pick one. Maybe you know the volume. You can find out what the pressure is. Okay, so that's Boyle's. You can do the same, by the same logic, of course it's a different constant. You have initial conditions equal to final conditions. So this one is equal to that one, right? You don't even have to know this. That's irrelevant. As long as you know three of these, you can find the fourth one. Okay? So, what's next? Well, let's see. We've held these two constant, investigated those two. We've held these two constant, investigated these. So along comes Avogadro. And Avogadro held, excuse me, Avogadro held this one constant and this one constant and investigated volume versus number of moles. So what did Avogadro find out? Well, if he changed the number of moles and held the temperature and pressure constant, then what happened to the volume? As the number of moles increased, the volume increased. So it's also a straight line. So that means if this is a direct relationship because it's a positive slope, then that's equal to volume divided by moles. And by the same logic, we can say that volume over moles, the initial condition is equal to a constant. Final condition is equal to that same constant. So V1 over N1 equals V2 over N2. Okay, keep myself on track here. The PowerPoints don't include this, but you may have seen this part of the discussion in the video. So this is Boyle's, this is Charles, this is Avogadro. The part that's missing from the PowerPoints that I'm sure I included in the video was the combined gas law. So we know the relationships here, each of these equal to constants. And we notice where they are in a mathematical expression. These are in the numerator, these are in the denominator. So what we can say is pressure times volume is in the numerator, and temperature moles are in the denominator. So those four factors give you a constant value. We can let those vary. It's a little messy. This is more convenience for calculations. So also, in this case, 1, 1, 1, 1, 2, 2, 2, 2. So this is before and after during an experiment. And if you know these factors and three of those, you can find the fourth one. But the value of knowing PV over Tn or Nt is equal to constant, or this one's equal to that one, is that all you have to do is hold two of these constant, and you get those laws. Right? Suppose we hold temperature in moles constant, you get Boyle's law. If we hold pressure in moles, we get Charles' law. And if we hold pressure and temperature constant, we get Avogadro's law. We can derive another law here that I don't have a name for. If you hold temperature and volume constant, you get pressure in moles, or a direct relationship. So if you hold temperature and volume constant, but you increase the number of moles, you'll get an increase in pressure. So this is the combined gas law. Okay. All right, so now all of these laws are valuable if you know before and after conditions. Okay. But if you don't know, if you only know what's your state right now, you don't know what happened before, you don't know what's going to happen afterwards. What do you do with that? Well, we can use the combined gas law as our jumping off point. So if these values, PV over Tn, are equal to a constant, then we can solve the equation to make it linear, put everything in the numerator. Right. So we'll just take this section here, move it over there. Okay. Now we get a law, an equation that we can use to determine any one of these values if we know three of them, plus the constant. Right? If we know this one, and that one, we can find out how many moles it is, as long as we know what that is. So we need a fixed value for this constant that does not change. These change depending on the conditions of the experiment. But we need a value for this one, and we're going to give it a special letter, R. And actually, it's written, more often you'll see it like this. PV equals N R T. So there's your constant. And here are your variables. We just need to know what R is. Well, the one we're going to use is 0.08206. But we need to know what are the units, right? When you have a constant value that's going to be inserted into an equation, you better know the units, because the units of the constant tell you what units you need for each of the variables. Otherwise, they won't cancel. So if we solve for R here, well, this is it right here. PV over NT equals our R. So for this particular value, pressure needs to be in atmospheres, volume needs to be in liters, this is moles, and this is K for temperature. So that's why the units here are typically given as liter atmospheres per mole K. Okay, and if you plug that value in here, then you can see that K's on the bottom here, and on the top here, they cancel. Moles on the top, moles on the bottom, they cancel. And opposite sides have to be on the same, have to be in the numerator. So there's your atmospheres, there's your liters. So this is the value we're going to use for our gas laws. If you use this equation, which is the ideal gas equation. Okay? The difference between these laws and this law is you need to know before and after here. Here, you don't need to know before and after. All you need is values for 3 of these, and you can find the 4th one. So when you look at it, when you read a word problem, you look to see, is this a before and after type problem, or is this a state problem? What is it right now? And that tells you whether to look for one of these, maybe this one, a combined law, or use this one. There are also references in problems to, I'll put it over here, STP. And that's not a gasoline additive. Standard temperature and pressure. Standard temperature and pressure for gases, as temperature is 0 degrees C, which would be what? 273 K. Right? And pressure is 1 atmosphere. So if you read a word problem, it says the conditions are STP, standard temperature and pressure. That's what it means. Now this is only for gases. When we're talking gas problems only, standard temperature and pressure, well, the pressure is always 1 atmosphere standard. But for gases, it's 0 degrees. I think that was chosen early on because it's very easy to establish 0 degrees as a standard temperature. I mean, you just need to encase your vessel in ice water, and you've got it pegged at 0 degrees. But for other reactions where we're going to study, including reactions with solids, liquids, gases, all mixed together, if it says STP there, the temperature changes to 25 degrees C. But I'll remind you of that one when we get to it. For the gas problems, that's STP. Let's see here. That's ideal gas. Okay, one more law. And then, see, up to this point, we've just been talking laws, right? This is what happens. We don't know why. We just know it happens this way. Then once we get through with the next law, Dalton's law, then we'll move to theory, which tries to explain why all these things happen. Okay, so there's, yeah, I'm going to need more room, so I'm going to have to erase these guys. Because I don't have any of that board on the video. I have to stay on this board. Dalton's law. Anybody remember Dalton? What else do we know about Dalton? Didn't Dalton come up with the atomic theory?
Yeah.
He proposed all matter was made of atoms, small, indivisible particles. Okay, that wasn't the only thing he was famous for. The Dalton's law of partial pressures tells us that when you have a mixture of gases, the total pressure that you measure from that gas, that confined mixture, is equal to the sum of the pressures of each individual component. So the total pressure is equal to the pressure of each of the gases. pressure 1, pressure 2, on out, however many you have. So what would be an example? The air we breathe, right? So at sea level, not where we are now, we're a half a mile high, but at sea level, the total pressure would be 1 atmosphere, right? So if you determined the pressure of oxygen, which is roughly 21%, and nitrogen, pressure of nitrogen, then you would have most of the pressure accounted for. There would just be one other factor, and that's the pressure of argon. Then everything else is a minor component and contributes almost nothing to the pressure. So we've accounted for the lion's share of pressures by adding up the pressure of oxygen by itself, the pressure of nitrogen by itself. Let's see, this would be 78%, this would be 21%, and this is about 1%. So using that logic, this would be 0.21 atmospheres. This would be 0.78 atmospheres. And this would be 0.01 atmosphere pressure. Add those up, you should get 1 atmosphere. So that satisfies the conditions of Dalton's law of partial pressures for the air that you breathe at sea level. A practical example or a story. The astronauts, originally, the ones that went up in Mercury, Gemini, and Apollo, their cabins were only pressurized with oxygen, pure oxygen. And since we knew the partial pressure of oxygen in the atmosphere, we knew that all they needed was 0.21 atmospheres of pressure in the capsule. Now, there were some other factors involved, so it wasn't exactly 0.21 atmospheres. I think it was probably, well, let's see, what would that be? 14.7 atmosphere, PSI, excuse me, is 1 atmosphere. So what's 0.21 of that? So that's about 3.1 PSI. So I know from reading reports that they actually pressurized the cabin to 5 PSI. So they went a little above on their oxygen. And that's the way they did everything until, I'll better leave that there, until Apollo 1. Where 3 astronauts died sitting in their capsule before they even got blown into space. All they needed was a short, and they got one. You know, John Glenn says the only thing that bothers me about this spacecraft is it was built by the lowest bidder. So the lowest bidder built the spacecraft, and they got a short in there, faulty wiring. And with that pure oxygen atmosphere, the astronauts were incinerated. Yeah. So after that, they started adding nitrogen into the atmosphere. It took a little extra engineering. The reason they did it was it was cheaper and lighter to just put pure oxygen in there and not deal with nitrogen. Yeah. So now when they mixed the nitrogen in there, that made the air less flammable, because flammability is dependent upon concentration of the oxidant or the flammable component. Okay, so enough of that story. Dalton's law of partial pressures. Okay, so if we know the total pressure, say you measure the total pressure of a mixture, and you happen to know the partial pressures, or the percentages, right? We can associate percentages, molar percentages of gases with their partial pressure. Then the percentage of each of those others leaves an unknown, one unknown. We can solve for it. And we use that as a practical approach for measuring gases as products of reaction. I'm not sure if no, I didn't put that in here. I think I just drew it. Maybe I drew it on the board. About the experiment where you submerge your vessel in water, and it's filled with water, and then the gases formed by the reaction are channeled into that container, and it displaces the water, and you measure the amount of gas collected. Did I show that in the video? Maybe not. Okay. So this is a practical example of Dalton's law of partial pressures. So there you got your water, and here's your vessel. Let's say, maybe like this. And let's just say the vessel is graduated. Right? So you can measure your volume. And then you have your reaction vessel over here, and it produces a gas. And as it comes in here, it bubbles to the top and starts filling it up. Okay, so you can measure the volume and the pressure. Well, by the time it reaches that level, and you can move this up and down. So if you move it to where this level is equal to that level, then the pressure inside the vessel is exactly the same as atmospheric pressure. Right? So that's the total pressure, as long as you match that level to this level. Okay? So you can find the total pressure there just by looking at your barometer. Then you can measure the volume. So you have the volume there, and that volume is, hold that for a second. The total pressure in there is divided between the gas that you're collecting, say the experimental gas, plus what else? You're bubbling the gas through water, right? So the other one is going to be water vapor. Right? So what you need to do to find out what is the actual pressure of the gas in there that you're collecting is you got to be able to subtract out that pressure for water. And fortunately, we can do that. They're charts. Right? All you need to know is the temperature of the gas. And the chart will tell you what's the partial pressure of water vapor trapped over water at a given temperature. Right? So then we can get that one, and we can solve for this one. Then you know the actual pressure of the gas you're interested in, the gas product of the reaction. Okay? So what else can we do? Well, once we know that pressure and we know that volume, we also know the temperature, right? So we can find out how many moles of gas are in there. Right? Because we know this one already. That's one of the state situations. Right? We got the pressure from Dalton's law. We got the volume from direct measurement. We got the temperature from direct measurement. R is a constant. We can solve for how many moles of gas are in there. Now, why would we want to know that? Because if we're studying this reaction, reaction equations are written in terms of numbers, not masses. So you need to know that as a product. So this reaction produces a gas. You may know what it is and you may not know what it is, but you can tell how many moles there are there. You know what you put into the vessel, so you can tell how many moles of each of the reactants there are. And that helps you, at the very least, tease out what reaction is actually occurring here. Or if you already know what the reaction is, then you can confirm that the mole ratios are what you say they are. Or you can say, maybe I don't know how much I put in here, but if I know what came out here, I can back figure to what I put in. Right? You know the mass. It's easy to find the mass of your reactants. And if you know the moles here, then you can work backwards to the moles there and ratio the mass in moles. Maybe you want to find out what's the molecular weight of one of the reactants. You can do that. So as my dad used to say, you jump on your horse and ride off in every direction. Okay, Dalton's law. Let's see. That's Dalton's. I gave some examples here. One really fun one was nitroglycerin when it decomposes. It's one of those slides. Okay, now we can go to the kinetic molecular theory. This is going to try to explain why all this stuff happens the way it does. Let me see, did they associate a person with that? Yeah, I didn't. So we'll let that slide for now. The kinetic molecular theory. Kinetic. Let's see. Now, why would this theory be important? Besides the fact that it explains why those laws happen the way they do, once we've established this as a viable theory, then we can port it over to other phases of matter, liquids, solids, in conjunction with gases, and use it to explain phenomena that occur only in solid matrix, or in liquid matrix, or in solutions, right? So it's like a jumping off point. Okay, so what are the factors that are important? What are the postulates of the kinetic molecular theory? One, large numbers of particles. Those particles could be, as far as gases are concerned, they could be individual atoms. They could be diatomic atoms, like some of our elements are. Or they could be molecules. They could be, big gaseous molecules. So they could be atoms. They could be diatomics. Or they could be molecules. But there are lots of them. Now, why is lots of them important? Because we cannot track individual molecules. So what we need is a statistical average. So we need large numbers. That way the average brings the theory closer to reality. So I want to put these, I could put them up there in the order that's in my head, but I'd rather put them in the order that's in your document. So the other is particle size is much, much, much smaller than intermolecular distance. Okay? So there's lots of empty space there. And I've been saying that from the beginning. That's why you mix two gases together, you always get a solution. Because there's plenty of room in there for everybody. They only meet one another occasionally. The next one is these particles are in constant, rapid motion. They're always moving. And at room temperature, that's a valid statement. The only time that particles, oh, got somebody zooming in. Zach is zooming in. Oh, do that. Okay. Well, more impressed by Zoom. Okay. I see you, Zach. Can you hear me?
Yeah.
Good deal. All right. Let me see. I want to bring this back up. Otherwise, it's not going to record correctly. How do I do that? There we go. Because if I leave Zach up big and me small, you're going to have trouble seeing the writing. Okay. No, I think there's a variable I need to set. No. Gallery. Pin video. Turn that down a little bit. Sounds like something I don't want us to hear. Okay. Particles are in constant rapid motion. The only time that particles would not be in rapid motion, or motion at all, absolute zero. 0K. And since we can never get to 0K, they'll always have some motion. But at room temperature, how warm is that compared to 0K? 173 degrees. Well, room temperature is hot, like gases. So, that's in rapid motion. And since you have lots of them, they're in motion, their average values, their average effect is felt. So we don't need to know anything about the individual particles in order to apply the theory. The next one is obvious. Particles collide. If they're all moving fast and randomly, then they're eventually going to collide. So what do they do when they collide? They transfer momentum, yes. So if two of them are coming straight on, and they're the same mass, say we have a gas that's only a single element or molecule, they come at each other at the same velocity, then their momentum is going to be transferred in opposite directions. Come in at an angle, then you've got a vector problem. So with lots of particles, that calculation can become unwieldy really fast, even for the fastest, biggest computers. So these particles collide, and in fact, here's the first derived explanation based on the theory. Measured pressure is due to collisions with the container. Okay? So when if those particles did not collide with their container walls, or each other for that matter, we wouldn't be able to measure pressure. Because what's pressure? Pressure is a force per unit area. We wouldn't have any force if we had no collisions. So the only way that we can measure pressure is that those particles collide with the walls of the container. And if we substitute for part of the walls of the container a device that responds to those impacts, that's how we measure pressure. Okay, and then I know there's one more. I'm going to switch these into order. Because the particles collide, collisions occur. Is that two C's? Does that look right? Collisions occur without interaction, without, well, that's a bad word, without attraction or repulsion. What we mean by that is the only type of interaction that these particles undergo is what you would see from billiard balls. They just bounce off one another, right? They don't come close, and once they get close, they're attracting one another or they're repelling one another. This is an ideal situation, right? We know that that's not true. We know that gases, particles do attract one another or repel one another. But the theory says that in order for the theory to work, we have to first assume that there are no attractions or repulsions during a collision. Then, after we've established that and established that it works in most situations, then we tweak it a little bit with these other considerations to get closer to reality. Okay. And then the last one, which I took out of order, the definition of temperature. Temperature is proportional to, does everybody know that symbol? Sort of an infinity with the tail chopped off. Temperature is proportional to the average kinetic energy, right? The average kinetic energy of the particles so if the particles are bigger or moving faster, then we will register an increase in temperature. Right? So for a confined gas, and there are no chemical reactions taking place, but for a confined gas, then if the particles start moving faster, they're doing that because the temperature is increasing. If the temperature decreases, we'll slow them down. Now, you can complicate that with chemical reactions in which you change the numbers and the sizes of your particles, right? Or you can introduce into your vessel a gas of a different size, right? And if you maintain the temperature constant, then if the particles, let's say for argument's sake, the particles are bigger than the ones that are already there, if they're at the same temperature as before, then the newly introduced particles will have the same kinetic energy. But kinetic energy, throw a little physics at you. Kinetic energy is equal to this for individual particles, 1/2 times their mass times their velocity squared. So if the kinetic energy is constant and the mass increases, what happens to the velocity? Decreases, right? It's a product. This one times that one is a constant, right? So like I said before, with Boyle's law, one goes up, the other one has to go down. So if the mass increases on the introduced gas, but the temperature is constant, then the velocity has to go down. But the kinetic energy remains constant. Okay? Let's see. So the kinetic molecular theory of gases can be used to determine the kinetic energy of individual particles. And we used balls. I think they were probably 5 kilograms. That's probably a bowling ball. Maybe 11.5 or 12 pounds, something like that. I tried bowling once or twice, but I was playing saxophone at the time, and every time I went to the bowling alley, I came back, I couldn't play for 3 or 4 days. It just wrecked my hand, so I stopped bowling. And priorities. Okay, so we're going to use this theory to explain some of the behaviors. And the next set of slides focuses on the kinetic energy, because the kinetic energy is related to temperature, which is integral to our previous gas laws. But the illustration I just gave introduces more moles, right? We introduce a new gas in there, we introduce new moles, so the pressure is going to go up. Why is the pressure going up? Because you've got more particles in your container smacking against the walls. And they've all got the same kinetic energy as they did before, but there's more of them. So the pressure is going to go up. Okay, more force per unit area. Volume, if we let the volume increase, we put more gas in there, then you're going to get more, let's see, I can't go down there. So let me make a little room right in here. If your vessel has a piston in it, right, and you've got a constant pressure on it here, and if you put more particles in there, and we allow this piston to move, then you put more particles in there, it sits there, you put more particles in there and they've got the same kinetic energy as they did before, and more particles are going to be more force on that piston, which causes the piston to rise. And as it rises, that spreads out the gas inside. So the number of collisions against that piston actually decrease as you rise in volume until you reach an equilibrium point, where the force that was pushing it up is now balanced again by the pressure pushing it down. So I'm trying to explain these variables in terms of the kinetic molecular theory. And it's all real simple. It's just lots of particles at a temperature with kinetic energy are smacking against each other in the walls. That's the whole thing in one sentence. I find it helps to reduce complex thoughts to just simple ideas. I mean, if it was good enough for Einstein, it's good enough for me. Einstein was famous for thought problems. He would take complex situations and just devise real simple experiments. I mean, just so simple a 3-year-old could think of them. Like, what happens if you're in an elevator and the elevator is going and it's dropping, you're dropping with it. How do you know it's moving? If you're inside the elevator, you don't know, right? Because you don't feel any force. But if you're outside the elevator, you can see, oh yeah, they're both moving together. So it's that type of simple experiment that Einstein was famous for. And then he would go sit for hours and work out the math. Okay, so that's what I'm trying to do here, trying to explain this very simply based on these premises that are part of the kinetic molecular theory of gases. Okay, so one application had to do with diffusion rates, and that was Graham's law of diffusion. Sometimes it's called effusion, but they're basically the same. there's not enough difference between them for me to try to explain, because I don't think I could do a good job of it anyway. So what does Graham's law of diffusion say? Is this where you start having trouble with the concepts? Yeah, that's perfectly logical. Another concept that we have to consider is the kinetic molecular theory of gas says that these particles are all moving with, they're rapid, there are large numbers of them, and their average kinetic energy is the same. But that doesn't mean that every one of them has the same kinetic energy. It's an average, right? So what kind of average is it? Well, it's not your arithmetic average, right? Where you just take their velocities and average them together and then say if they're all the same gas, then you use the kinetic energy formula. That never works. What you have to take into account is the fact that no, that's not right. Kinetic energy is down here. This is numbers of particles. They're in, the best estimate is they're usually distributed in the bell curve, kind of like student grades. So the average is most students, and then you have a few out here and a few down here at the D and F end and the A end, and then the C and bottom B's and upper D's are right in here. But for particles, the lion's share of particles are in here. But what we need to do in order to use kinetic energy as a measure, and Graham's law in particular, is come up with a way of an average kinetic energy that represents this. If we just took the average velocity and used the kinetic energy formula, we would get, let's see, I'm looking, what direction would our error be? Our error would be low. So we would be saying the average kinetic energy would be down here somewhere. If we just used average velocity, and that's what that bar means, just statistical terms. A bar over a value of a variable means average. Okay. This is what you would get if you used this average V, so 1/2, and we're going to assume that all their masses are the same. If you use that average velocity times their the single mass, then you get a certain kinetic energy, and it would be a low estimate. So we need something for that V, or for this kinetic energy. It works both ways, because once you know this one, then you know that one. That will give us the average kinetic energy that is accurate. So the solution to the problem is root mean square. Right? Root mean square. In English, that means the square root of the means of the squared values. Okay? So what we do is we take all the values and square them. Then we take the average of those squared values. Right? So what happens when you have, let's use velocity as an example. So what would the values be? Meters per second, right? And then you square them. So you get meters squared per second squared as your average value, the units of measure. So we can't report a velocity in meters squared per second squared. That doesn't make any sense. So we have to take the square root of it again, and that reduces it back to meters per second. But in the process, we have arrived at an average value that will give us kinetic energy that's right dead center. Root mean squared, okay? You probably don't realize it, but you use root mean squared every day. Whenever you flip a light switch on, whenever you plug in your computer or power cord, you're using root mean square out of that socket. That's alternating current. What does that mean? Well, that means it varies over time. 60 cycles per second. It goes up one hill, down the other, and back here. So it does that 60 times a second. What's on this axis? Voltage. This is time. So what we want is some way to give you 120 volts. This is the direct current equivalent of alternating current. This is the actual voltage. So it goes up to, I measured it one time, I think it was around 140 volts this way, and this is negative 140 volts. Right? So it varies that much. But the root mean square value of all of these is 120 volts. Okay? That's just to illustrate the fact that root mean square is not a foreign concept. You just didn't know it yet. Probably, unless anybody in here knew that beforehand.
Yeah, I did. I weld and stuff sometimes. Like, if you try to use an AC with welder, it's so much harder than using DC.
Yeah.
Just because the power, it keeps coming in and out, in and out.
It switches back and forth, yeah, right. Yeah. Okay, so that's root mean square, practical uses. Now, how do we calculate with it where particles are concerned? That's where Graham's law comes in. Graham's law says that this root mean square, and U here means velocity. So the root mean square velocity of our particles is proportional not just to temperature, but to the molecular weight of the gas. Right? So what happens? Well, if the molecular weight goes up, what does that do to this term? Makes it go smaller, right? Because it's in the denominator. So that means as the molecular weight goes up, velocity decreases, as long as you hold temperature constant. If the molecular weight gets smaller, then the root mean square velocity of the particles shoots up. So compare. Say we have hydrogen gas at one temperature in one vessel, and nitrogen gas in another vessel at the same temperature. Which one's moving faster? On average, the hydrogen, because it's smaller, right? So, but one of the examples in your thing, and I think there's an animation in here that goes with it. Let's see, what do they use? Hydrogen chloride and ammonia. So in this container, in this tube that's transparent so you can see what's going on, we put a cotton ball here with hydrogen chloride gas, right? That's not hydrochloric acid. That's hydrogen chloride gas. It doesn't become an acid, remember, until you put it in water. Right? So HCl gas, and you can get that. Just take concentrated hydrochloric acid and open the container or pour it into a beaker and stick it under a hood. And you'll see fumes coming off of it. Those are hydrogen chloride gas. Okay? You don't want to breathe them because they'll choke you. Or if you breathe long enough, of course, they'll kill you. On this side, in our example, we put ammonia. And then they're going to migrate for the center. Okay? Now, which one moves faster? Well, all we need to know is what's the difference in their mass, right? So this one's 3545 plus 1.01, 6 or 6. Great. So that's grams per mole. Okay. And this one is 14.01 for ammonia and 3 times 1.01 for hydrogen. Right? 1704. Right? So this one's the lighter gas. This one's the heavier gas. Right? So where are they going to meet? Over here, in the middle, over here? Over here, because that was moving faster, right? It's going to be racing across here, and this guy's just kind of keep waking up. And somewhere in here, they're going to combine. And you're going to see a cloud form. Because when ammonia and HCl react, they produce ammonium chloride, which is a solid. It's finely divided, so it still stays suspended. And that's how you can see where they meet. And you can measure the distance that this one travels, measure the distance that that one travels, and ratio them. You can do that with any two gases, right? So if you know the molecular weight of one of them, and you measure the distances that they traveled in ratio, you can find out the molecular weight of the other one. Right? Not directly from this equation, we have to derive an equation, and that's what one of the slides here has done for us. So what it says is, we'll use these as our examples. So the distance that ammonia travels divided by the distance that hydrogen chloride travel is proportional to the square root of the molecular weight of HCl divided by the molecular weight of ammonia. Okay, so there we have an equation in 4 variables. All we need is 3 of them, and we can find out. This is just a ratio, right? So this could be any length of tube. The ratio is going to be the same, because while this one's moving this way, that one's moving that way, they meet somewhere in the middle, and the ratio of these two distances is always the same, as long as we don't change the temperature. And then if we know one of these, we can find the other one. Okay? You may have encountered that in the review document, using that formula. You just need a way to tell where does that occur. This one's easy because it forms that cloud. Sometimes you might have to suspend some indicator in here, right? So that the indicator will change color when these two meet and react. Or you might not be able to see it visually. You might have to illuminate it with a black light and see it. Or whatever else you need. That's a practical matter of designing your experiment. But we use this reaction where hydrogen chloride and ammonia meet to see if our fume hood's working. You just take a beaker of ammonia, which stinks, and a beaker of concentrated hydrochloric acid, which stinks, and you set them close together like that, and when the gases come up, they mix, and they form that cloud. And then you can see it move in your fume hood. Now, that's the pretty way to do it. I mean, it's neat, but you really don't have to do that. It's just demonstration purposes. You just need a chem wipe, and you just tear off a piece of chem wipe, hold it up there, and see if it goes whoosh. Okay, or you tape it to the edge of your sash When you move your sash up, you can see it go like that. But it's a good ooh-ah thing to show. Like I used to have grade school and high school kids come through for show and tell in our lab, and I'd have different demonstrations set up. You always get some oohs and ahs. Okay. Okay, so one of the last slides gives you an example. We're measuring the molar mass of an unknown and then comparing it to this chart. We know that ammonia is going to react with any type of halogen hydride, which is hydrochloric acid, hydrobromic acid, hydroiodic acid. It'll react with any one of them, so that's why you have that choice there. And then you use that formula to calculate the molar mass and compare it, and you can decide which one's which. Now let's see, that formula should be in useful information. Just checking to be sure. Back it up. Here we go. Okay, at the bottom of the page, we have we have the pure Graham's law formula, and then right next to it on the right, we have this one. Now, in this case, we use distance, but for this formula, it has ER. What does ER mean? Effusion rate. How fast is it moving? Right? So it moves, you set your timer, say it moves this far in that amount of time, effusion rate, the ratio is the same either way. Right? But sometimes effusion rate is more convenient to measure. Right? Particularly if you're doing, here it is. If you're doing separation of uranium fluorides in this plant, I got a little picture in here. I used to live in Oak Ridge, right? And they had 3 major processing plants for nuclear materials. One of them used effusion rate, right? They would, under high pressure, they would take uranium fluoride, UF6, and it would be a mixture of uranium-235 and 238 primarily. So we want the 235. That's the one that fissions, but it's very, very low concentration. So you just run it through a filter, and the ones that are going through fastest are the lightest, 235 fluoride. So it would concentrate on this side, and then we'd have another one concentrate again, concentrate again. You just keep pushing them, and you would recycle what was left behind so that you would keep the pressure at the desired level and just send it back to the beginning and put it through again, right? So down here, you would increase the concentration. If you were going to make a bomb, you'd want it to be probably 90% or 95%, 235. If you were just making fuel for a reactor, you could stop at maybe 5 or 10%. But using a fusion rate, that's how this plant worked. And see how big it is. I mean, it was huge. So we needed lots of those Teflon plates, thousands of them, to get the desired effect. Because the difference in mass between 235 and 238 is very small. And that begs another question, why they use Teflon? Well, because uranium hexafluoride is extremely corrosive. You could not make your filters out of stainless steel. It would just chew them up. All the fluorides are that way. So they needed a material that was unreactive. And about that time, Teflon came along. DuPont made a fortune supplying the the federal government with this product. And then later on, they decided to slap it on frying pans. There are other ways to separate, that are now more efficient than this. Right? So now the preferred method is ultracentrifugation. That's what the Iranians are using ultra centrifuges, spin it 100,000 RPM, and the ones that are the heaviest sling to the outside.
Separate out.
Right? And then you do it again. You just bleed off this versus that one, and take the one that's depleted and send it back to the beginning, send it through again. But you send the enriched one to the next centrifuge, and they just have stacks and stacks and stacks of it. And so what do you do for a rogue regime like that? Well, you send some malware in there that causes their centrifuges to act erratically. It unbalances them, they destroy themselves, and it takes them several months to rebuild their program. So that's what the Israelis did that once. So cyber warfare, that's where things are going. So learn how to program, and you get a job. You have to see Patricia Hoover about that. Okay, any questions so far? That's all the, I took longer than I wanted to, but like I said, we got time. Then we can go in and look at the review document. Yeah.
So we had the distance of ammonia and the distance of hydrochloric. How did you know to put hydrochloric on the bottom? Because it was the larger one?
Yeah, well, intuitively speaking, right, the larger one is going to be proportional to its molecular weight. So if you move it over here, and then this one will be proportional to that one. But mathematically speaking, we just solved the equation in forms of a ratio. We just took this one and we ratioed this one molecular weight of one of them ratio to the other one, and their velocities are going to be different. And velocity is what? Distance over time, right? So you have distance over time ratioed. Let's do it like this. So if we have, no, let's not do it that way. Let's do it this way. And then this one would be velocity. Well, let's do distance over time. Distance of HCl over time. And time's going to be the same, right, for both of them, as seconds. Time. So the time's going to be the same for both of them. And we're ratioing this one over time. So the time's going to cancel. And then we combine these two, and the R's and T's cancel. And then when you, if you take a square root of a value divided by a square root of value, you can combine them, square root of the whole thing. So this is in the denominator, in the denominator. So the denominator of the denominator is the numerator. So that flips this one up on top. So that's what inverts them. Right? So now it's on top, and you got distance. So that's the quick version. Rather than take another half hour to explain it. You can rewind the video. Okay. So that's the overview. Now, I'm going to leave that there because we need to reference that when we work problems. So now we can go to the review document. Oh, we can take a break. Does anybody need a bathroom break?
Yeah.
Yeah, let's take a 5 minute or so. There are no smokers in here, are there? Okay. Takes them a little longer. I don't know, how long does it take to burn a cigarette? Yeah, between 5 and 10 minutes.
How I understand this part because I understood that how these two things are.
Oh, because this is in the numerator and that's in the denominator. Well, we just cancel.
Then you'd switch them because that's how the math works. But well, it looked like
Oh, if you're going to do it step at a time.
it looked like this for our key. Well, because basically that means it's folks.
Yeah, this would be 1 over that.
Yeah.
Yeah. 1 over that. Yeah, there you go.
And
And the
that's
same thing in the bottom of this one.
Because that basically means they're both for square root, both square root.
Right.
Okay, and that's why they switch.
And then you take the square root of the whole unit because the square root of this divided into the square root of that is the same thing as this divided into that square root of the whole thing. Then since they're both inverse, you just flip this one from the bottom
Flip it
into the
back,
top
flip that back, and then,
and it comes into the numerator.
okay.
Yep.
Thank you.
All right, let me stop that. There we go. Got one that shows up better. Black. Okay. So, before I get started, are there any in here in particular that you want to look at? So that we can be sure and cover your concerns before I start just going down the line. You'll notice, I think this one has. Does this have some, no, that must have been a different class. I was looking for ones designated as bonus up front. Well, there's one that's left deliberately blank. Did I explain that? Why I left those blank?
Which one?
Oh,
I'll make you explain that one.
it's number 54.
54?
Yeah. The reason for that is originally I had set up that problem and then worked out the problems in longhand. And then I realized we didn't even cover that in this chapter. So instead of going back and renumbering and doing these all over again, I just said that one's blank, and then I chopped it out of here too, I think, 54. So, yeah, 54 I just removed.
Yeah.
It was kind of short, so all I had to do was blank it out in Acrobat and then write over it. If there are any others like that, then they're for the same reason. 86 actually was a duplicate. No, 86 is valid, but I redid it on the next page. So I blanked out that side and put it on the next page. But that was a valid problem. Okay, enough of me. Do you have individual problems that you want to deal with before we lose sight of working other problems? Or I can just start working, we can run through it, and if something strikes you, then inject your problem and we'll get to it.
Probably, for mine would be probably the STPs.
Okay.
This,
Example, which one?
I'm gonna say 55.
Okay. Let's see what 55 has to offer. Argon has a density of 1.78 grams per liter at STP. 0 degrees centigrade, 1 atmosphere.
So to find STP, 0 Celsius over 1 atom.
Huh?
How do you find the STP?
No, this is temperature and this is pressure. They're not related. These are values that are associated with standard temperature and pressure.
Okay.
That's the standard temperature and that's the standard pressure. So when it says STP, that's what they mean.
Okay.
It's just giving you these values in shorthand. Do you still want to work out the problem?
Sure.
Okay. How many of the following gases have a density at STP greater than that of argon? Argon has a density, okay. So I like to be consistent with the way I work these, so I'm going to look at the way I work this problem. All right. So we've got argon is the one that we're given. Then we have chlorine, helium, ammonia, and nitrogen dioxide. So what we need to know is, first of all, the density that's given for argon is 1.78 grams per liter. And the molecular weight for argon, actually, let's do molecular weight here first. Is 39.95, right? 39.95 grams per mole. And that was not doing too well. Another one. So there's no law against calculating molecular weights for the rest of them, right? So what's the molecular weight of chlorine? Well, it's diatomic, so it'll be 2 times this value. 3545 times 2 is what? 70.9. And helium is 4.00. And these are all grams per mole. Ammonia, we just did that 1 minute ago. It's 17 something, wasn't it? 1703?
Yeah.
And then NO2 is 1401 plus 32. Can I do that in my head? Hurts. $46.01? Okay. So we know these because we were given that. So this is a valid calculation that we did. But we need to find out what's the density in order to compare the densities of each of these to that one. So what I've done is a little algebra. What's the definition of density? Equals mass per unit volume, right? And if we solve that, well, let's see. What's the definition of molecular weight? Is mass per mole, right? Grams per mole. Okay? So we're going to combine these two equations because we know what this is. And we're going to use the rest of it to determine what that is, or compare them anyway. So how do we combine these equations? Well, we look what our target is. We want to know the density. So we want to substitute something in here that keeps density intact. So it looks to me like if we solve this one for mass and put it in there, then we'll get an expression for that. So solve this one, mass is moles times molecular weight. And then we substitute this one right there. So density equals moles times molecular weight for that term, divided by volume. Okay? So what does that say? If we have the same number of moles in the same volume, we hold these two constant, then the density is going to be proportional to molecular weight. In other words, as the molecular weight increases, density increases. Right? This one goes up, that one goes up. So if we say that, then all we need to do is say, compare the molecular weights. This one's bigger. What was the question? Which one's larger? How many were larger? Density greater. Oh, and the other key is we're at standard temperature and pressure. So that means the number of moles by comparison is not going to change, and the volume is not going to change. So this one's denser, and this one is denser. So the answer is 2. 2 of them have a higher density than argon at standard temperature and pressure.
You just found out by knowing that those two were bigger than 39.95?
Mm-hmm.
Because
we had to prove it first. This is proportional to that. As this goes up, that goes up, or as that goes up, this goes up. So if the molecular weight goes up, then the density has to increase. Because we're holding the volume and the number of moles constant. That's not changing. The only thing we're allowing to change among these is the molecular weight. And we just showed that if we increase that, we increase the density. So far, so good? Or is that give you a few minutes for your head to stop spinning? Okay. Or, if you're not too confident in your math, just know all other factors being equal, higher density equates to higher molecular weight. Just remember that. I mean, if you have to memorize something, then go ahead and memorize that. We just proved it, but that'll give you the right answer. Oh, I forgot to write. What number was this?
55.
55? Okay. For the benefit of the video. Okay, any others? That one's not doing too well either. How about this one? Purple.
How about number 4?
Right. Some retrograde motion. Which of the following would represent the greatest pressure? So number 4. And we've got these. They're E. Okay. We're given 0.680 atmospheres, 517 millimeters of mercury, 11.4 psi, 62,106 pascals, and 14.1 inches. Okay, so the first thing you have to do is decide, because you can't compare. I mean, you've got apples and oranges and bananas and kumquats and lemons. You can't compare them until you get them in the same units.
So would you compare them all to 8?
I suggest, yeah, going to atmospheres. So what's the conversion here for millimeters of mercury to atmospheres, right? Because we have to cancel that one and leave atmospheres. So how many millimeters of mercury in an atmosphere? 760. Okay? We'll do the math in a minute. This is the hard part. So what's the relationship here? Pounds per square inch to atmospheres. Well, one book says 14.69 and one says 14.7. For our purposes, that should work. because we've only got 3 significant figures anyway. This one is a little trickier. How many pascals in 1 atmosphere? That, hopefully, I've included that in the useful information, so let's check to be sure it's there. Okay. Down the left-hand side, it should be somewhere along there. Yep. 101,325. 101,325. 1 atmosphere. How about this one? Inches of mercury in 1 atmosphere. I think it's 2992, but let me check to be sure. Inches of mercury. Yeah, 2992. And these are all values that are given in useful information. And just to beat that horse while it's dead, that useful information table and anything in the back on this review document, it will appear on the exam. So you just need to know where it is and how to use it. Question?
So how to get to 760 millimeters mercury of mercury? Because
That's an identity. 760 millimeters is 1 atmosphere. Is it not in the values?
Oh, it is. I just didn't see it.
Okay. Okay, now just do the math. Right, this one's already in atmospheres, so we just need to do the rest of them. So we have to divide this number by that number each time. Henry Ford, right? It's an assembly line. 760. So this one is 0.680, rounded off. This one is 11.4 and 14.7. This is 0.776 atmospheres. 62,106 divided by 101.5. This one is 0.613 spheres, and 14.1 divided by 29.2. And this is 0.471 atmospheres. So then I have to go back and look at the question. Which is the greatest pressure? Well, let's see. These are equal. That one's bigger. The rest are smaller. So that's the biggest one. So is that the answer we gave? Yeah, C. Okay? That's just, you know how to use conversion factors. That's the whole point of that one. And where to find them, right? These are, what was it? Fantastic beasts. And where to find them? Only mine don't live in a suitcase. Okay, any others? 7, okay. A physics experiment. I'm sorry?
7, and I'm not confused if somehow got it right.
Because you don't remember, you don't know how you got it right?
No.
A physics experiment is conducted at a pressure of 14.4 kilopascals. What is this pressure in millimeters of mercury? Okay, this is a multi-stage conversion. So this is number 7 for the benefit of our video viewers. Let's see. You still there? Maybe not. Okay, so we're starting at 14.4 kilopascals. We know that our conversion factors, we don't have a kilopascal conversion in here already, I don't think. Let me check just to be sure. I think our conversion is actually pascals. Yeah, there's no kPa in here. So if we're going to use that conversion factor to give us millimeters of mercury, we're going to have to convert this to pascals first, right? So how many kilopascals is represented by pascals? So which one's bigger? A kilopascal is 1,000 times a pascal, so that's bigger. So if the unit is going from bigger to smaller, then the product should be going from smaller to bigger. So 14.4 kilopascals, 1 kilopascal is 1,000 pascals. So this is a case where you have to know what that K stands for. What does it mean? A kilopascal is a bigger unit of measure than a pascal. So you need more pascals to make up one of these. And how many more? 1,000 times more. You're taking this kilo and just putting it right up there. Kilo is 1,000, put it up here. Okay? All right, now that we know that conversion, we can use this one to go to atmospheres. And that was 101,325. 101,325. Okay? So we've canceled kilopascals. Now we cancel pascals, leaves us with atmospheres. And now we go to millimeters of mercury from atmospheres. So what's the conversion there?
760.
Right. 760 millimeters of mercury. Now we've done all the hard work. That's the brain work. The rest of it is crunching numbers. Of course, you have to crunch the numbers correctly, right? Common mistake is saying such and such divided by something, and it should be the other way around. So you got to say it right. Say it right in your head. This number divided by that number times that number, right? When you put it in your calculator. Now, if that's 1, you can ignore it because it's not going to change the answer. So 14.4 times 1,000 divided by 101,325 times 760. So I get 108 millimeters of mercury. Is that one of the answers?
Yeah.
Yeah, okay. I have to check sometimes because as many times as I've used this review document, I still come up with errors. Everybody good for that one? Now, I have some students occasionally, I haven't heard that from many of you, but some students like to use the picket fence. You know what the picket fence is? So this keeps your numerator away from your denominator. So this would put 14.4 up here, and that would put this one up here, and this one down here. And you just do the same thing for each one. I use parentheses, but there's no reason why you can't use the picket fence. I mean, if it helps you keep things in order in their proper place, by all means use it. Okay? I'm not saying you have to. It's just an alternate way of doing things. Okay, that was 7. We got another half hour before lab time, which doesn't mean, I mean, we can bleed into lab time, that's all right. Let's see, those are definitions. What about, I don't know, 16? A balloon has a volume of 2.32 liters at 24 degrees C. The balloon is heated to 48 degrees C. Calculate the new volume of the balloon. So, what are you given? That's a good place to start. A balloon has a volume of 2.32 liters. Right? At what temperature? At 24 degrees C. Okay? But it's going to change because we're going to heat the balloon. Now the temperature becomes 48.0 degrees C. So what kind of problem do we have here? A state function or a before and after? Right. So that's the beginning. That's the final. And then the question should be, calculate the new volume. So this is the one we want. All right. So we decided it's a before and after. So what formula, what law are we going to use for this one? Charles' law. All right. And what form will it take?
V/2. V equals.
Something like that. Okay. So the next thing you need to do, by writing it up here this way, we've established what's before and what's after. So that hopefully eliminates the possibility of putting this one in for 1 and this one in for 2, in which case you get the wrong answer. And since this will be a multiple choice test, the designer of that question probably has included an answer that accounts for that mistake. So if you see your answer in there, it doesn't mean it's right. It's only right if you did it right, right? Okay, that's how sneaky multiple choices are. Okay, so we know where everything goes, but are they in the proper form? Not yet. Temperature has to be Kelvin. Right? So we need to add 273 to this one, add 273 to that one. This is 297?
Yeah.
Okay. How about this one?
341.
Okay. Notice I don't put a degree mark, okay? Doesn't have a degree. Okay, now we can plug in the numbers. So V1 is 2.32 liters, and T1 is 297. Okay. V2 is our unknown, and our temperature is 321. Okay. So now all you have to do is solve for V. You got it?
So would it be 2.50747?
Let me see. Yeah, 2.51. Liters. Notice that when we move this one over here to do the calculation, the K's cancel and leaves us with liters. Okay? Any of these before and after, as long as you get the temperature right, it doesn't matter what the other units are. Right? Because it's a ratio. Right? The K over here is going to cancel. That rule doesn't hold for degrees centigrade. If you use degrees centigrade in there, get it wrong. It's got to be K. But for the others, this could be milliliters. You know, we could say 2,320 milliliters. Then the answer would come out in milliliters. Okay.
How did you calculate that?
Oh, this one, just up here, times that one.
Okay.
This one's already in the numerator, so we can just leave it there. And this one times that one divided by this one gives us the answer.
Okay.
Now, as long as you're using the ratio type equations, then the only one you have to be sure about is temperature. The rest of them can be any units you want, or whatever's given. But if you get to a state function where we're using this one, this dictates what the units are. And they have to be converted to K, moles, liters, atmospheres. Now, there are many versions of R, right? But we're using 0.08206 because it gives us the units that we want. If you stick around, when we get to problems that involve energy, like joules, there's another gas constant that we use for that one, which includes joules rather than liters and atmospheres. Those two go away, and they're substituted by joules, plus the effect that it has on the constant value itself. So it's different. It's 8 point something or other. But it should be in here too. Just a confusion. Yeah, I got different R values there. Down the middle of the page. Yeah.
Can you go over number 17?
Oh, yeah, sure. 17. Now, I think the review video that I made in February that goes along with the lecture video might cover different problems. So you can look at that one also. But this one will be available for the problems that we covered today. You say 17?
Yes.
Okay. Let's see how I explain it. Just to be consistent. Okay. All right. 17. We've got a sample of gas in a container on a comfortable spring day, yada, yada. The Celsius temperature suddenly doubles, and you transfer the gas to a container with twice the volume. If the original pressure was 12 atmospheres, what's a good estimate for the new pressure? Okay. So what are the factors that we're dealing with here?
The volume.
First one I see is temperature. That doubles. Then volume changes. And pressure. So we've got before and after for each one, right? And the question is, what's a good estimate for the new pressure? That's the one we want. So what do we have for these? Well, let's see. It doesn't actually tell us what the temperatures are. It just says we go from this one to this one in degrees Celsius. Okay, the temperature doubles. So if we start at that one, the new temperature is double the Celsius temperature. The volume is some value. It doesn't matter what the units are because we're going to use, this means we're going to use a ratio, so they're going to cancel anyway. And twice the volume. Okay, so the new volume is twice the original volume. And the original pressure is 12 atmospheres. Okay. So remember the combined gas law, which we're given these that change. So which one is constant? Those two are constant. Moles are constant. Right. So if we use the combined gas law, this one goes out. It doesn't change. Right? So now we have P1 V1 over T1 equals P2 V2 over T2. We want to answer this question right here. We want that one. So let's solve for that one. P2 equals what? This one comes over here. Right? And this one comes over here. Okay? Now, before we plug in any numbers or algebraic equivalents to numbers, we need to look at this. No, this. All right. Convert this to Kelvin and convert this one to Kelvin. Now we can plug them into our formula. So what's P1? We've said P1 is 12. 12 atmospheres. What's V1? V1, we gave it a Y. What's T2? It's 2x plus 273. And what's T1 is x plus 2. And then V2 is 2y. There we go. Now, no, I'm explaining it a little different than in here, which is not bad. I mean, gives you another perspective. It's just the way that my brain's working today. Okay, so let's take our factors. This is that divided by that, which means that's gone. All you have now is 1 over 2. Okay? So let's say P2 equals, let's factor out these two. And then that puts 12 divided by 2, right? This one divided by that, because that's equal to 1. We factor that, we cancel out y, leaves a 1 here, leaves a 2 there. So this 12 divided by 2 covers that one, that one, and that one. And these are pulled out over here. So this together equals 6. Now, 17. What's a good estimate for the new pressure? Okay. For this one, you don't have to do that calculation. What you need to do is look at the choices. 3 atmospheres, 5.5 atmospheres, 6.4, 12, and 15. Okay. Process of elimination, test taking techniques. If we increase the pressure, temperature, we've doubled the temperature, what should happen to the pressure? Well, the effective temperature should increase the atmospheres. But what happens to if we increase the volume? That should decrease the pressure, right? So this one, by doubling, the effect of doubling would give you 3 atmospheres by itself, right? But increasing the temperature, we did not double the temperature. We doubled the Celsius temperature. We didn't double the Kelvin temperature. right? So, now that would be 6. Or not point that. It would be, we would expect it to be in that neighborhood. Well, first of all, are we going to increase the pressure to 15 atmospheres? We increase the temperature, but we decrease the volume. So it can't go up that much. Right? 12 atmospheres is what happens if we do nothing, but we did something. Right? So now we have to choose among these 3. So if we were to double the volume, we should get 6 somewhere in here. So we're not going to double the temperature. We're only going to increase the temperature slightly. So increasing the temperature increases the pressure, right? So starting from 6, the only way to go is here. Did I lose anybody? Okay, I see a head, a good head. Or do I need to explain it again? Do you understand why 15 and 12 won't work? Okay.
No. I don't understand.
You don't understand that? Okay. We decreased the volume, right?
Yeah.
But we didn't increase the temperature very much. We doubled the Celsius, but we didn't double the Kelvin. We doubled the Kelvin and doubled the volume, we'd end up back at 12, right? But we didn't double this one. So it can't be 12. That means we did nothing. Or we doubled the Kelvin and doubled the volume. If we did that, then we'd end back at 12 because they cancel each other out. But we didn't increase the temperature enough to go from 6 to 15, right? We know we didn't double the temperature, the Kelvin temperature. So there's no way we can get to 15 from 6. Right? So that's why 12 and 15 don't work. Then we have to say, okay, now if we double the volume, then that gives us 6. What effect does the temperature have? Well, if you divide these two, it's like 1 point something, 1.1 maybe, or 1.2 or 3. So from that point, we're starting at 6. So that eliminates this one. Which way do you go, that way or that way? Well, if you increase the temperature, you got to go that way. So that's why this was your best choice. Okay. It's a critical thinking logic question, basically. I mean, there are actual values there, but you only need them for decision purposes, right? If we had been given actual values here and here, then you could go calculate it. You know, find exactly what the value is. Now, did I claim to have done that here? No. Good. Because that would have been a false claim. There's not enough information to exactly calculate that number. You have to logically choose among the 5. And those are the kind of questions that usually give students the most trouble. Most can learn how to use a formula. There are only a few that are, I mean, just completely lost and can't use a formula even then. But most can use a formula, get your answer. It's these logic questions that give you trouble. Separate the sheep from the goats. Okay, that was 17. Any others? We got 10 more minutes before we start using up lab time. Yes?
22. Can you explain to me what's the one where they're all the same? Is it because of the STP?
Let's see. Oh, yeah. Right, 22. Actually, 22 through 24 use the same conditions. We're just asking different questions. So the temperature and pressure, standard temperature equals that. Standard pressure equals that. Volume is given at 1 liter. And each of the gases in A, B, and C are ammonia, nitrogen dioxide, and nitrogen gas. First question, number 22, is which contains the largest number of molecules? It's sort of a trick question. Just see if you know the laws. What did Avogadro say? It wasn't just Avogadro's formula or law that we're concerned with. What Avogadro actually said, and let's use a picture. Each one of these is 1 liter. So say we're just comparing two of them, you know, for argument's sake. The temperature of both of them is the same. The volume is the same. Yeah.
Because they're both at STP.
Yes. They're all gases at STP, and we're also told that that volume is 1 liter. Same volume, same temperature, same pressure. Avogadro said, if those conditions are the same for both, then the number of moles, or the number of particles, of each gas is equal. That was Avogadro's revelation that solved huge problems toward the close of the 19th century. European companies and research groups were just hitting a brick wall. They could not explain reactions properly because they didn't know this concept. 1865, oh, is that the year after the Civil War ended? I think.
1964.
Yeah, 64 ended.
Yeah.
Mathematics was 64 sometime. 65, all these scientists from all over Europe came together at a place called Karlsruhe in southern Germany, Bavaria. They went there because it's beautiful scenery, you know. Scientists don't like to stay busy all the time. So they met at this at the university there, trying to solve this problem. Why were their reactions going wrong? They didn't understand why you put so many grams of this one together and so many grams of that one, and sometimes you get grams of this one, and sometimes you get grams of this product, and sometimes they didn't know why. So they came together to try to figure it out and solved nothing. Fortunately, there was a young chemist standing at the door as everybody was leaving with reprints of a research paper he had published. His name was Cannizzaro from Italy. He had based his work upon Avogadro's concepts. And he was handing out these reprints, so everybody politely took one from him. You know, I guess some of them threw them in the trash and some of them took them home. Enough of them read them when they got back to their universities and companies, and the light bulbs started going on and say, that solves everything. This concept tells you how many particles you have in each one. Because if you have this many particles here, this many particles here, they will be equal as long as those are equal. But if you change those, you're going to get a difference in the number of particles. Right? That way, you can gauge the reaction, because reactions are built upon the concept that you're not reacting masses. You're reacting numbers of particles. Moles, 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 moles. And all they knew up to that point was mass, 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 mass. And that wasn't telling them anything of value. But once they got this, and then they went back and looked up, every paper has references at the end, cited publications, then they found Avogadro's work. They went back and looked at his work too. And then latched on to his law, Avogadro's law, and put it together with others, because by that time we had all of those laws together. Then they could solve their problems. You know, and then the company started making money right and left because they solved those problems. They didn't have to guess anymore. And research groups were able to, I mean, it was just skyrocketed from that point. So what's the moral of the story? Economics drives everything. If there wasn't money in it,
They ain't gonna do it.
right, they would not have sent their scientists to that meeting. Now, of course, their scientists had to explain why they went there and came up with nothing, but then they had that paper. They said, yeah, but we did discover this one thing, you know, and thank God I went to that meeting. Next time we have a meeting, you can send me that one too. By the way, it's going to be in Cancun. And after that, we're going to have one in, let's see, Hawaii. And then after that, let's go to New Orleans during Mardi Gras. Okay. I know how scientists think, especially research scientists. Okay. The floor is open. Yep.
30.
Okay. Okay. Good choice. So what are we given? We're given a volume of oxygen gas, right? And the volume is 1.72 liters at a temperature of 27 degrees centigrade and a pressure of 800 torr. The question is, how many oxygen molecules are there? So we need to know how many moles, and then we convert moles to molecules. But how many numbers of oxygen molecules are there? So what kind of problem is this? It's a state function, right? So we need the ideal gas equation. Okay. Now we got to check our units. If we're going to use that equation, our units have to conform with the constant. So this one's good. That one's not. Excuse me? Yes. And convert this one to atmospheres. So what's a torr? Yeah, 1 torr is 1 millimeter of mercury, right? So the conversion here is the same as millimeters of mercury, 760. Let's see, this one is 300 K. Yeah, 300 K. And this one is 800 by 760. 1.053. Now, I know I used too many there, but I always do that. I don't throw away decimals until the very end. So we're looking for this one. So we just solve our equation for that, or you can just plug the numbers in and then solve it. But I like to solve it ahead of time. So that means this is equal to this one divided by this one. Okay? So now we can plug in our numbers. Pressure is 1.053 atmospheres. Volume is 1.72 liters. R is 0.8206 liter atmospheres per mole. Okay. And temperature is 300. There we go. So the number of moles should be 1.053, 1.72, 100. I get 7.357, that's 10 to the minus 2 moles. And then to find the answer here, we've got to convert it to numbers of molecules. Right? So what's the conversion factor for moles of molecules?
Isn't it 6.02 times 10 to the second, 23rd, sorry.
Right. And this would be molecules per mole. Technically, I shouldn't use N, I should say numbers of O2. So let's see, 6.022, next 23. So I get 4.43. Now I'm going to round it off to 3 significant figures because of that. Molecules. So let's see if that's in the answers. Looks like it's A. Okay? So the point I'm trying to emphasize, among others, is be methodical. Yeah.
I was meant to say number 50.
Oh, not 30?
Yeah, sorry, I got that mixed up. Yeah. it's
Okay. Did anybody benefit from that?
Hey, I did too.
Okay.
Thank you.
It's nice to know that I'm not spinning my wheels. But that was a good choice because we've only done before and afters up to this point. Unless, is 50 another?
This is elastic, I don't know.
Oh, okay, so this is different. All right. So this is based upon information at the top of the page. So you have to go all the way up there and see. Now, in a testing environment, that information would be given individually for each question, right? It wouldn't apply to a whole bunch normally. And if it does, I'll be very specific about which questions it applies to. Okay. All right, so in this case, 50, we're given 1 liter flasks of each one of these at 0 degrees centigrade and 1 atmosphere. So temperature equals 0 degrees C, pressure equals 1 atmosphere. I like to write information out on the board. And volume equals 1 liter. Okay. Now for 50, the actual question, for which gas are the collisions elastic? Oh, well, okay. I don't even need to write those up there. What do we mean by elastic? That's your question, isn't it? Okay. An elastic collision is one in which the kinetic energy after is equal to the kinetic energy, I should say, total, is equal to the total kinetic energy before the collision. Okay, there's no loss of energy. So what happens is when these two particles meet, right, they collide, they impact one another, they may compress and then bounce off. But in the process, as they are completely stopped and then they reverse direction, at the point where they stop, right before they reverse direction, all of that kinetic energy is converted to potential energy in some form. But then as they leave one another, the total kinetic energy of both in that system is preserved. That's an elastic collision. Okay. An inelastic collision, and it varies, right? But an inelastic collision is part of this kinetic energy before is converted to some other form, right? So I guess you could say if a chemical reaction occurs, right, you've converted it into another form. Or if they're just solid spheres, if they strike one another and the kinetic energy afterwards is less, you wonder, where'd that energy go? Because energy has to be conserved. You can't create it, you can't destroy it. Right? So more often than not, the potential energy that was stored before they sprang apart, some of that potential energy is converted into heat. It's thermal energy, most often. So this one would be less than that one, and the difference would be potential energy of heat. Well, actually, that's not potential energy. And you can argue both ways. Well, let's just say it's converted into thermal energy. Oh, and to answer the question, according to the kinetic molecular theory, all of them are elastic, right? They're all elastic. That's central to the, remember what we said, there's no interaction, no attraction, no repulsion. They just act like billiard balls. And within that concept is the fact that the collisions are elastic. They perfectly preserve the kinetic energy.
I have a question.
Yep.
Would that, so that won't apply to, even if it's STP, or if it's not STP?
Oh, anytime.
Anytime.
Yeah, under any conditions. Right. Right. If you say the collisions are elastic, that applies under any conditions. Unless we say they're not. It's true unless we say it's false. I see a hand go up over here.
How would you know that it was under the kinetic molecular theory? Or is that just...
That governs everything we're doing.
Okay.
Yeah, in this chapter. Yes.
53.
All right. The mass of 1.12 liters of gas Y at STP is found to be 6.23. The molar mass of gas Y is. Okay, good choice. All right. So we're given 1.12 liters of gas Y. Gas Y has a volume of 1.12 liters at STP. So temperature is 0 degrees or 273 K, right? And pressure at 1 atmosphere. So we don't know what this one is. We're not given that one. But we are asked, what's the molar mass of gas Y? I abbreviate as molecular weight. Okay. So the molar mass of gas Y, what are the units of molar mass? Grams per mole, right? Okay.
Can you just repeat?
Oh, I left out mass. Excuse me. Mass is given as 6.23 grams. Okay. So if the question is, what's the molecular weight? We need to know this and that, right? We know that it's given to us. So we need to calculate how many moles there are. Can we do it?
You use the ideal gas?
Ideal gas equation, right? So we need to solve for this one. T over R T. So pressure is 1 atmosphere. I'm going to leave out the units because we've made the conversion here, so we know they're going to be right. R, not yet, volume, 1.12 liters. R is 0.08206. And temperature is 273. So the number of moles is just the solution to that, which is 1.12 and 0.08206, 273. I get 4.9995 times 10 to the minus 2 moles. So we know, so whatever X and Y is here. That's a bad choice. A and B. So the mass is 6.23 grams, and the moles, this one. Grams per mole. So if I say 6.23 divided by that number, I get 125 rounded off grams per mole. Let's see, is that a choice?
Yes.
C. Okay. So I guess that's basically a dimensional analysis problem with gases thrown in as a factor. Let's see. We have done in this class so far percent by mass to empirical formulas to molecular formulas. Yeah. So when we're given those problems, we're given the percent composition. That gets us to empirical formula. But then you need to know the actual molecular weight to go the rest of the way. This is one way to find it. Okay. There are numerous ways to find the actual molecular weight of your compounds. This is just one of them. There are others. We'll do one in Gen Chem 2. Stick around. We'll use colligative properties. Freezing point depression is one way we'll find the molecular weight. Another is by titration. If it happens to be an acid or a base, you can use titration. We may do that one this. Yes.
I have a question. So you said that you can find molecular formula with that one?
Well, yeah, if you're given the percent composition data along with this, then you can do the empirical formula, find out what its empirical weight is.
But you can only do that with gas?
Oh, well, this is for this one, it would be a gas, yes.
Oh, okay. But it can actually be used for anti-fire?
This is reserved for gases.
Or just a gas?
Yeah, or compounds that can be converted into a gas without destroying them.
All right.
Yeah, and there you go. There again, that's experimental design. You know, which one works. But this is just one method. Okay. Two. Okay. I want to take a look at 56 also, right after this one, so don't let me miss it.
All right.
The mass, same conditions as 53, except we're asked for density of the gas. Okay, so for this gas at STP, standard temperature, 273, okay, pressure, 1 atmosphere, volume, 1.12 liters, and the mass is 6.23 grams. The question is, what's the density? So So go to your definition. Density is mass per unit volume. And then it's a good idea to look at the answers to see, all right, what are the units that they're looking for? They're looking for grams and liters. Right? So this is going to be in grams, this is going to be in liters. So do we have the information we need? Yep, we have grams, we have liters. So it's just a matter of plugging in the numbers. Whatever that happens to be. Let's see, it should be 5.56 grams per liter. That's typical for gases, grams per liter. For solids, it's more likely that you will see units of measure grams per cubic centimeter.
And that is the same thing as grams.
Milliliters. Grams per milliliter, right? It's the same. Yeah. Okay, 56 I wanted to look at. Any questions about this one before I erase the evidence? So this is one of those logic problems. Which of the following is the best qualitative graph of pressure versus molar mass of a 1 gram sample of different gases at constant volume and temperature? So volume is constant for this problem. Temperature is constant. Okay. So we've got pressure and moles. Mass is the same. So mass is constant also. So what we're looking for is the best graph of pressure versus molar mass.
How do you know mass is the same?
Because it said so, 1 gram sample. Molar mass. We want to know what the graph looks like. Okay. Let me see how I explain this one so I can be consistent. This is going to be one where we combine equations, because what we want is an equation that gives us the relationship of pressure to molecular weight. So what do we know? Well, we know this one. Okay. We know molecular weight equals mass per mole, and we know, well, those are the only two we need. Because this one has molecular weight, and this one has pressure. So that should be enough. So, let's find molecular weight is going to be our Y. So we're going to leave this one here, Y equals something. And then we're going to convert over here to fill in what we don't have here, which is this one. Right, so we want this one in terms of moles. N equals PV over RT. So we substitute this one right here. Molecular weight equals mass divided by PV over RT, and the denominator of the denominator is the numerator. So this is RT mass over PV. And if we're going to let pressure vary, then everything else has to be held constant. That's a constant. Yeah, we have to hold temperature constant too. Because in order to find this relationship, everything else besides pressure and molecular weight have to be constant. So So that's a constant, 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 constant. Right? So those taken together are constant. So it'd be like that. So molecular weight equals K over P. All right? So let's put K on one side. Right? K equals molecular weight times P. Okay? Now, here's the real thinking part. Is the product of two variables equal a constant, is it inverse relationship or direct proportional? Think of Boyle's law. Boyle's law is a constant equals pressure times volume, right? And what kind of relationship is that? Inverse, right? So, as a matter of fact, when you put it this way, it's going to be a hyperbola with negative slopes at various points. So does everybody know about instantaneous slope? No. It's the tangent, a straight line tangent on a curve at any point, right? So at that point, well, it's not close enough, but that's the slope at that point. That's the slope at that point. That's the slope at that point. Okay, that's an instantaneous slope. But regardless of how they change, they're all negative, right? And negative slope means inverse relationship. And we always get an inverse relationship when a constant is equal to a product of variables. Unlike Charles' law, which is a constant equals a quotient of variables. Quotients are always direct relation, and they're positive slope. So the answer to that one is 56. The closest one, I shouldn't have said none of these. The closest one is D, because D represents an inverse relationship. All right. Technically speaking, if you gave me E, I'd have to give you credit for it. In fact, that is the answer. But if you gave me D, yeah, you could probably argue that your answer is right.
Yeah, because it is a negative slope.
Yeah.
It's all wrong there.
And that's the whole concept. Negative slope is inverse relationship. Okay, anybody else? Others? We can get on to, yeah. 58. Okay. 58. We're given the reaction. Looks like it's balanced already. That's a gas reacting with chlorine gas. Yields nitrogen gas and 6 hydrogen chloride gas. Okay. You react 5 liters of ammonia and 5 liters of chlorine. Measured at the same conditions in a closed container. Calculate the ratio of pressures in the container before and after. Okay. So this one is a problem in Avogadro's law. I don't know why it took me so many steps here. Maybe I was trying to explain everything. Oh, I see. I see why. We had to find a limiting reactant. Right? So Avogadro says if all conditions remaining constant, the number of moles is proportional to the volume. In other words, if you change the number of moles, you change the volume. They're proportional. So if we have 5 liters here, we have the same number of moles. We have the same number of moles here as here. Right? The same volume under the same conditions, so the same number of moles. So we can argue this in terms of volume. So in this case, for every 2 liters of ammonia, we need 3 liters of chlorine. Okay? So if we react all of the ammonia, how much of the gas do we get over here? Well, 5 liters of ammonia. Let's see. Let's do it this way. We're going to convert to nitrogen first. So it's 2 to 1. 1, 2. So we get 2.5 liters of nitrogen. Right now, what we're doing is determining limiting reactant. So how about chlorine? Chlorine. How many nitrogen do we get? That's 1 nitrogen for every 3 chlorine. Right? So 3 divided into 5 is 1.7. 1.66, 1.67 liters of nitrogen. Right? So chlorine produces the least amount, that means it is limiting. So we're going to use up all of the chlorine. It's gone. But we have some of this left over. Right? So when the reaction proceeds, we're going to produce that much nitrogen from that chlorine. How much hydrogen chloride do we produce? Well, let's go from the limiting one. HCl, 6 for every 3 chlorine. Right? So that's just 2. 10 liters of HCl. Okay, so based on the limiting reactant, there we go, and that would make this excess. Okay, so now we've got this many liters of nitrogen, this many liters of hydrogen chloride produced. How many liters of ammonia do we have left over? Right, because we want to find out what's the total amount after the reaction. So we've got this, that's gone. But how many liters of ammonia are required? Right. So 5 liters of chlorine. We're going to convert that to ammonia. So that's 3, and this is 2. Okay. So it ought to be twice that number. Liters of ammonia used. So how many are left over? 5 minus. Did I do that right? I didn't do that. 1.7. 1.7? 1.67 liters remain. Right. Okay. So that's the amount of gas we have after the reaction. Then, what's the question? Calculate the ratio of pressures in the container. So, Avogadro said that the pressure before related to the moles before is equal to the pressure after it related to the pressure afterwards. Okay? They're directly proportional. But the question asks us for the ratio of the pressures, right? So it's terms of, let me get this wording correctly. Calculate the ratio of pressures P final, P initial. This is P final, that's P initial. So it would be that one divided by this one, which means that one came over here. And I'm just flipping it. So what happens to the moles? Well, N comes over here. Sorry. N2 comes over here. 1 there. Okay? Now, also, we have to understand that the number of moles is proportional to the volume. Right? Because if you have an increase in volume, everything else being equal, you have an increase in the number of moles. Right? So this ratio is also proportional to V2 over V1. So this is final, initial, final, initial, final, initial. So we need to know this relationship because we don't have moles. And we don't want to have to calculate moles. Right? But we do know volume. So the ratio then, this whole value is a ratio of what's the final volume. This one plus that one plus that one. All right, so this one's 3.333 plus 13.33. And the initial volume was 5 plus 5 is 10, right? Oh, so that's 1.33 is the ratio. Now, did I get it right? Good. It's always good when I come up with the same answer that's on the key. Now, did I lose anybody? We've done limiting reactant, haven't we? Okay. I'll be sure we've covered these concepts before I start throwing them at you again. All right, so we were given the balanced equation, given the conditions, that much and that much, and we were told that constant volume, temperature, and understanding the relationship, volume of gas, all things being equal, is proportional to moles. So these ratios also stand for volume under the right conditions. And we have those conditions. The conditions are stable. So we know that we can ratio, we can determine limiting reactant based on volume, not just moles. So that makes these calculations possible. Otherwise, you'd have to convert that to moles, and that would take the rest of the test. You'd never get around to another problem. Okay, I know there are a whole lot more problems in here. Let me look at the back. Short answers? There's some short answers. Maybe I'll look at the short answers. And then we can get on to talk about the lab. Okay. Excuse me. Number 128 looks like the first short answer that I come to. A room is 16 feet by 12 feet by 12 feet. Right, so we've described a cube. Well, not a cube, but a cube-like. Would air enter or leave the room if the temperature changed from 27 degrees to -3 degrees, while the pressure remained constant? Determine the volume of air that moved in or out of the room. Well, we can intuitively
Figure out the volume, figure out the temperature. We can change that to Kelvin.
All right, we're given a room that is 16 feet by 12 feet by 12 feet. And the temperature goes from 27 to -3. See, pressure is constant. Okay. And what they want to do is what volume moved in. Volume difference is actually what we're looking for. Okay. We can do some intuition here first. If the, think of Charles' law, temperature and volume relationship, pressure and moles stay the same. If the temperature goes from 27 degrees to -3 degrees, it's decreasing, right? If you decrease the temperature, then you should decrease the volume occupied by that gas. So that leaves a vacuum, a part of the room that has no gas in it. So the gas is going to move into the room. Air is going to move in because we decreased the volume occupied by the gas that was there before. Now we just have to decide how much is that. Let me see how I approach it. That's the logic part. Let's see how the math goes in. Okay. Okay. So what we want to do to find the volume difference is we want to know the volume initial minus the volume final. That'll tell us the difference in volume. That answers. So what's the initial volume? Right there. Right? 16 times 12 times 12 equals 144 times 16. I remember my multiplication tables. 2,304 cubic feet. 304 cubic feet. So we need to convert this to what? Well, look, depends on the answer. What is it looking for? Cubic feet. Determine the volume of air that moved in. It doesn't say convert it to anything. So we can go cubic feet. All right, so we're going to use Charles' law. So V initial over T initial equals V final over T final. And find out what the volume was after the process. We know what the volume is before, 2,304 cubic feet, right? So now we want to know what's the volume after. All right, so I forgot to do one thing, didn't I? Got to change it to Kelvin. So this one is 300, and this one is 270. Right? Okay, so what's the final volume? It would be the initial volume times final temperature divided by the initial temperature. So the initial volume is 2,304 cubic feet. This is one of those ratios where you can use cubic feet because both of these are cubic feet. They cancel. And then final temperature, I should have put this, final initial is 270 divided by initial temperature, which is 300. Okay, so the final volume is going to be what?
2073.6.
3,073.
Oh, in 2000.
2,000. 2,070 rounded off, 74. Okay, so the difference, how much air moved in, is 2304. That's, yeah, final. 2074 equals, I think that's 260. 260.
Yeah.
No, 230.
Yes.
Close enough. Cubic feet. So that's how much cubic feet of air moved in from outside into the room when we change the temperature. Let's see. I don't want to run out of time because we do need to talk about the lab a little bit. Let's just look at 130 and say, how would you step this problem up? Or does anybody want to do that one? Or do you understand it well enough we can skip it?
I kind of like to try through.
Okay. So for 130, we want to calculate the density of fluorine gas. So density is mass divided by volume. And this is at 26 degrees.
When we convert that degrees and just Kelvin.
So that would be 299. And pressure is 755 torr. So that needs conversion too, doesn't it? And we need to know density. All right. Well, we're not given mass, are we?
What would the mass be for?
Actually, let me show you how the mass is going to be irrelevant. There's the density. Here's the molecular weight equals mass per moles, and then MRT. So if we're looking for density, we want to substitute something in here and here that we know. Right. So if we we change this one, solve it for mass, that's equal to molecular weight times moles. And substituting this one in here, we get density equals molecular weight times moles divided by volume. Okay. Molecular weight is equal to mass divided by moles. Well, we already did that, excuse me. So that's okay. Now substituting in here, let me see, that's where I did it. Yeah, we're going to solve this in moles. So this is N equals PV over RT. Substituting there, molecular weight times PV over RT divided by volume. We're not given volume, but look here. There's a numerator, there's the denominator. Volume's gone. Doesn't matter. R is a constant. Pressure, we know. Well, after we calculate it, we know it. Let me see if I got that already. No, I don't. .993. So pressure is 0.993, and this is the denominator of the numerator, which is the denominator. So we got molecular weight over times pressure over RT. Temperature is 299. This is 0.08206. Pressure is 0.993. That. And how do I get rid of molecular weight? Were we given that value? Oh, F2, thank you. So molecular weight equals 2 times 19, which is 38. It's 38. We have that one, that one, that one, that. Oh, that's the solution. Just do the math. It should be 1.54 grams per liter. Right. This is grams per mole. This is atmospheres. This is liter atmospheres per mole. K. K's cancel. Moles cancel. Atmospheres cancel. Grams per liter. Okay. Unless somebody has another problem we need to deal with, we will move on to lab. I'm still grading your last lab. Shouldn't take me much longer. Question? So you're probably wondering how big is this test? 65 points required and 32 points bonus. Lots of bonus. 65 points doesn't mean 65 questions. There are some 1 points. And see, there's some 3 points. There's a handful of 5 points, 1 10 points.
Chances always under about 50 questions.
Yeah, let's see. The required is 26 questions. And then the bonus is 9 questions. Okay. All right, let me put this.
Bonuses we have to work out.
Huh? Bonuses
We have to calculate.
Yes, show your work. Yes. I think I get your meaning. Otherwise, you just got a good memory. Or a good guesser. So remember the everything up through chapter 4 in your homework, you need to turn that in because I'm still counting that. But from chapter 5 on, the homework doesn't count anymore. We're just going by test grades and attendance. Wasn't that in this class? Yeah, that was in this class. Okay. Yeah.
So is that the chapter 4?
Yes. If you want credit for it. Okay. Yeah, you can't just leave it hanging. And then the points that would have been assigned to homework for each exam are being moved over to the exam column. So the weight for exams now is going up. But I think, I don't know why I think this. I think if you work all these review problems, right, you'll do well on the exam. Okay, so let's move on to the lab. Okay. Turning in laboratory techniques, that's good. Waters of constitution and hydration. I talked a little bit about this in lab last time we did it. Right? I showed you how to do waters of hydration, how to calculate how many moles of water were in the molecule. Right? Does anybody have any questions about that one?
So, the one with the sodium.
Oh, the sodium bicarbonate? Yeah.
I don't want to see that, because then it's just the calculations.
Say again?
Because you're supposed to figure out the other molecule. This is sodium plus sodium containing substance.
Yes.
So, how do you want to figure that? Because I just said that the last one, the one where it reacts like.
Okay. For that one, rather than go through the whole argument of scenario 1, 2, 3, 1, 2. Let's see. Scenario 1, throw that one out. Scenario 2, throw that one out. Scenario 3, is a possibility. Scenario 4 is a possibility. Okay, so 1 and 2, you can throw those out. And since I've given you the logic here, you don't have to put it in your report. But you do need to prove it's either scenario 3 or scenario 4 in this document that I handed out.
It's okay if I just leave that. Because the last part of the procedure says add 1 molar of boric acid. Does that work?
That technically, yes. If you show me the equation that leads to that reaction, because if you use scenario 3, then you should be producing sodium carbonate, Na2CO3. So scenario number 3 yields sodium carbonate as a possible sodium-containing compound. Scenario 4 leads to sodium oxide. Okay? So, what happens when you put these in water? Right. This produces produces this one. That one. Right. Sodium carbonate aqueous. It goes into solution. What happens to this one, though? It reacts and produces sodium hydroxide. Let's see, is that the only thing it produces?
Wait, one I have 2 H's.
Right here.
Never mind. You already had it.
Yeah. 2 hydrogens, 2 oxygens, here, and 2 sodium. Okay, so that's what happens when you put sodium oxide. If your sodium-containing compound is sodium oxide, it makes this. So when you add hydrochloric acid to it, what does it do? It just neutralizes it, right? It produces sodium chloride plus water. Well, two. Okay, no gas. But if you add hydrochloric acid to this one, what does it produce? It produces CO2 plus sodium chloride in solution. Let's see if that balances. No, it doesn't balance. All right, that's an intermediate step. Excuse me. Right, so there's your chlorine. There's 2 sodiums. There, trying to balance it. So 2 sodiums, 2 chlorines, 2 hydrogens, and a CO3. This is what acid? Carbonate, H become X, carbonic acid. All right, this one produces the gas. Okay, so that's the evidence for this one versus that one. Now, does that mean that there's not some of this in there? There could be some of this in there, right? But the argument is that in order to go from this one to this one, you need a lot higher temperature to decompose it to this one. And we didn't produce that temperature. And so you have a wide temperature range. And as long as you establish that this bubbles, then that's your compound. Now that's, excuse me? Yes. Now, I also put a discussion in here of quantitatively proving it. Okay. So if you, for instance, on page 3 of that document, I have those 2 blue boxes. And the first one says, if you start off with 2.5 grams of sodium bicarbonate, and you produce sodium carbonate from the reaction, and you need to write the reaction, sodium carbonate with heat produces what? Bicarbonate, excuse me. Sodium bicarbonate plus heat produces, you're arguing that the sodium-containing compound is sodium carbonate. So what does that leave you? You have expelled 1 carbon dioxide and 1 water. Right. So to balance that equation, we need a 2 here. That leaves 2 sodiums, 2 hydrogens, and 2 carbons, 1, 2, and 6 oxygens, 3, 4, 5, 6. So that balances this is what you're arguing for that one, right? So if you start off with 2.5 grams here, or whatever your value happens to be, right? You can calculate how many moles that is, right? So this is grams. So in my scenario, 2.5 grams translated to 0.02975 moles. 0.02975 moles. Once you have moles, then you can find out how many moles of this, 2 to 1, so it'd be half of that, right? So half of that would be 0.01488. to 1. So now that you know moles here, your argument is that if I convert this back to grams of this compound using its molar mass, then I should get a value that's close to the weight that I got after the decomposition. So if you use that to convert it back with 106.1 grams per mole, that's the molar mass of sodium carbonate. Then you should get 1.577 of this compound. Compare that to the value that you got, but using your actual values. So you put your actual values in there, do the conversion, because this is your argument. You're saying this is what it is based upon the bubbles. So based upon the bubbles, this should be the decomposition equation. And how do we know that it loses carbon dioxide and water? Because in order to go from here to here, it has to lose the hydrogen. And in order to lose the hydrogen, it also has to lose some carbon dioxide. But it can't lose both of them, or you don't have that molecule anymore. Right? Otherwise, you've got this one. Right? So you have to have that one. That's the only possibility under this scenario. So now back to the calculation. Use your number to find out how much of this would be produced. That's stoichiometry. Then compare that number to the number you actually got in your experiment. What was the mass of the decomposed sodium-containing compound? And it should be very close to that. And that is quantitative evidence for the progress of the reaction. Okay? That's why I put it all in this document, so that you probably heard every third word I just said, right? So if you go back to the video and the document, then you've got everything you need to finish the report. Now, since this is your first report, you may have questions about, what format. Well, that's why I gave you that practice format. You follow that format of the practice one, and it gives you, I want introduction or objective, I think it goes, and then some words about safety. What's your safety concerns? Then the procedure, what you actually did. Like approximately 2.5 grams of sodium bicarbonate were weighed into a clean crucible. Or you could say the crucible was prepared this way, then 2.5 grams approximately was weighed into that crucible. Can
we put a hypothesis section in it?
Sure. Yeah. So I want the procedure to be in passive, actually, third person. I don't want any I's or we's or you's.
Okay.
Third person, passive. That is, something was done. Not active like.
If we don't use I or we, because third person is going to hurt them, right? Stories and stuff. Is that okay if we put names? Like,
No, you don't need names.
Okay.
Because you're saying
basically
something was done.
Okay. Or put this here, right?
No, you don't say put this here, because that's understood to be you put this here. Yeah, that's second person. Okay? First person is I, we. Second person is you. Third person is it or they did something. No, don't say they. That's wrong. Don't say they. Say it happened. Okay. Passive, past tense. Past tense is important because you're telling me what you actually did in the past. So one thing you don't want to do is regurgitate the procedure out of the hard copy. right? If you looked at the rubric on that line, go to the very end, and it says 0 points. If I detect that you've regurgitated that procedure, you get no points at that point for that section, right? Okay, and that brings up another point. If you want to know what to put in your report, there are two approaches. Actually, it's good to use both. The rubric tells you what I'm looking for. Okay, so you look to the left, highest points. That's what you really want to get in the report. And the other is, if you write your report, and then you go back, you set it aside, and then you go back maybe an hour later and you read it and say to yourself, I can't do the experiment based on this report. If you cannot duplicate the experiment based on the report, then you've written it wrong. You've left something out. Okay? You need to be able to duplicate the work based on the report. That's the concept in a nutshell of publication. You publish your work, put it out there for everybody to see, and you argue your case based on the evidence that you've got in your report. That's what the conclusions and summaries are for. And then if somebody wants to argue with you, then they've got to come up with a better argument than yours. You know, it's like this. But the other scenario is, the other reason for writing the report a certain way is that any scientist that's reading your report understands what you're saying. It's in a format that they're familiar with. Plus, they know what you did to get these answers. Okay, and they can go back and do the same thing to see if they get the same answers. Right? They can duplicate your work. So, I forget where I was going with that one. Maybe a question would be good now.
Okay, in our safety part, do we have to put our safety part in the third person?
It's best. Yeah, it's best, but you don't have to. I'm really looking for procedure.
Just procedure.
Yeah, primarily in past tense. So you're going to have the introduction. You can throw in the hypothesis if you want. Sometimes the hypothesis is understood. Safety, procedure. Don't put your data in the procedure. In other words, when you say so many grams were weighed into the crucible, don't say the exact number. You just say approximately this much was weighed. You say the exact numbers for the data section. That's where the exact numbers go. Okay? And then you have calculations. So I want you to show me how you got your calculations, how you got your answers in the calculation section. And then you can also, and it's best for the reader, if you put this stuff in a table, right? Table format, then it's easier to find. You know, and the less frustration you give your instructor, the more likely you are to get a good grade in calculations. And then there might be some questions. Were there lab questions as part of this?
So where there was like
if there are questions, then you have a section there, like pre-lab questions, may just be called questions, or post-lab questions. Put those in there. You don't have to write out the question as it's given in the hard copy, but you should write your answer in such a way that the question is implied in the answer. Okay. And there may be some calculations there too. You can either do them right there, or you can put them back in the calculation section, in which case you would, in your question answers, you would refer to calculations.
Yeah, I did not calculations and explain them on which ones.
That's fine. Yeah, as long as I can find them, you know, then I won't be tempted to mark you off. Yeah. And then summary conclusions, right? And if you look at the summary and conclusions part rubric at the bottom, you'll see what I'm looking for. Right? That plus the reasonably good sample report. I mean, it wasn't perfect. I mean, you'll see some red ink on the sample too, but they weren't major problems. Okay, yeah.
So, okay, so this lab we had 2 parts to do, like the part 1 and then with copper sulfate.
Yes.
This one's sodium carbonate.
Sodium hydrogen carbonate.
Hydrogen chlorine. So could we do like 2 data sections, like where data
You should.
for part 1 and then do and do calculations for part 1 and then do data part 2 with the calculation?
Sure, that's fine.
Okay.
Yeah. Or you can put all the calculations in one, as long as you say this is part 1, this is part 2. I'm flexible there. I mean, I used to review publications, you know, papers that were going out for publication. They sent them to me and I critique them. Some of them were, I mean, these were supposed to be PhD scientists. And they wrote some pretty sorry reports. So I hit those with red ink too. Some of them were really good, you know, and those were the easy ones. I could just review them. Yeah, check, send it back. You know, some of them, fortunately not many, were horrible. You know, not just the experiment, the data, but what their interpretation of it was just completely wrong. I was going somewhere with that. Senior moment. It was important enough to dig it out. Oh, yeah. And when reviewing these papers, or even if I'm just looking up a published paper and reading through it, it follows that format. And after I read they usually have an abstract, so I'm not making you do an abstract because they're a pain to produce. You read the abstract and then introduction, and tells you, is this paper really going to give me information or procedures that I'm going to use for my work? Do I need it? So at that point, I say, nah, you know, I go on to another one. If it does, then I go to the methods, or the procedures. Sometimes they're called methods and materials. And I look at those. I say, okay, that's good, that's good, that's good. Okay, this refers to some other paper, so I got to go dig it out. Say, okay, all right, they followed that procedure. That's good. Then I can go to the data and say, if they followed that procedure, then their data is good, right? If their procedure is crap, then I throw it in the garbage. Don't even use it. All right, so that's where scientists go. Once they decide that a paper is worth looking at, they go straight to the procedure. They don't go to the conclusions. They don't go to the data. They go to the procedure and see if the procedure is valid. If the procedure is valid, then you go to the data. And then follow that with conclusions. You know, that's the order of operation for a competent scientist. Okay, so, oh, Boyle's Law. Are we ready to go to the next lab? Okay. Yeah, because we're about out of time, I think. Or are we out of time? 11:50? What was it? Let's see. 12:20. Okay. I thought I was out already. Okay, so next week, hopefully I'll have my vehicle back and all my tire pumps. So we can do Boyle's Law. So to do this lab, we need some type of contraption that will allow us to measure the volume as we change the pressure, and measure the pressure accurately while we measure the volume accurately. So
Pressure gauge.
yes, we're going to use a tire gauge, right? So if you've looked at the report already, you'll see that I have a 2-liter bottle and a tire gauge built in, right? So you can unscrew that cap and you can drop a syringe in it that's also capped off, right? We're confining it. Yes. I'm sorry?
Does 1 liter bottle say?
Oh, it should be a 2 liter. That's an important distinction. Right? It should be a 2 liter bottle. So our syringe is in here, and it's got a plunger there, and then it's got a nipple down here, and we're going to set it at a certain volume, I think 10 milliliters, and then plug that hole. Why do we plug that hole? Because if we don't, when we pressurize this environment, it's just going to push up inside here, and that syringe is not going to move. Right? We have not actually pressurized the gas in there in a way that we can read it. So we confine the gas, then we pressurize the vessel, and that pressure pushes down here on that syringe, and you'll see it drop. Okay, and you'll get down to between 1 and 2 milliliters probably by the time you get to 60 psi. And I use fresh bottles every time. I used to reuse bottles, but one of them blew up. So we use fresh ones. They're supposed to be good to 100 psi, easy. But if you pressurize and depressurize, pressurize and depressurize, you start developing little flaws in the bottle, and eventually it pops. It's kind of like airplanes. You know, when they go to altitude, they only pressurize at what, 5,000 feet, 10,000 feet, 8,000, something like that. That's why you go up in an airplane and say, if this thing is pressurized, why are my ears popping? Right? They don't pressurize it at atmospheric. They pressurize it at some altitude that's breathable air. Anyway, as you go up and down, you pressurize and depressurize, and the plane goes over time, right? So they have to go through periodic safety inspections to see if developing any flaws in the plane so it won't come apart in the midair. But anyway, we're pressurizing this vessel, and the pressure inside here is measured with your tire gauge, right? Right, so this thing's going to come out here and measure how much pressure is in there in psi. Right? So you ask yourself, how much pressure is actually on that cylinder? Well, it's the pressure that you measure in here plus atmospheric pressure. You got two pressures. You got the measured pressure plus atmospheric. Right? So we find atmospheric off the barometer that's in the lab. Right? So this measured pressure is going to be in psi. So convert that to atmospheres. Right? 14.7, 14.69, whatever. And the I should say barometric. Because using ATM, you think units of measure. So this is barometric pressure, then would be whatever it happens to be at that time. And our barometer measures in inches of mercury. So you convert that to atmospheres. We did that in one of our problems, didn't we? So just whatever the conversion, 2992 inches of mercury is 1 atmosphere. So use that. Then once you get them in both the same units, then you can add them together. And that's the pressure that you record in your table. So you're going to have a table with pressure and volume. This will be in milliliters. That's fine. This will be in atmospheres. And you'll have, the best way to do it is to pressurize it first. Then measure the pressure. And anybody who's done tires knows once you do that, it's going to go, you're going to lose a little bit, right? So measure the pressure first because you lose some in the process. Then look at the volume. Because if you look at the volume first, measure the pressure, the volume is going to change a little bit. So do the pressure first, then the volume. And you're going to fill in these values. But you're going to start from high pressure to low pressure. So say you start at 60 psi and you go down, I don't know, whatever the procedure calls for. I'm just making things up as I go along. And then you go down And the last one you take, now this is measured. So that's what you do in the lab. And then you'll have another column for total. So that's where you add the barometric to it. Right? Okay. So you're going to not atmospheric PSI. So what do you do for 0 PSI? Measure the PSI. Take the cap off. Be sure that it's equalized. Right? And that's your 0 PSI. Total then plus whatever atmospheric is, right? Okay. And for each one of those, you're going to get a volume in milliliters. Measure as close as you can get. Usually a tenth of a milliliter is doable. Down to, you can estimate that last one. One other trick, when you measure, these syringes are the best I've found, but they're not perfect. Right? So if you start at 10 mils here, when you get to 0, it's not going to be 10 mils. It's going to be like 9.7 or 9.8. So it tends to stick. And I know the procedure probably says lubricate it, which is okay. So we've got some lubricant you can put on it, some Vaseline or something. But even that isn't perfect. So we measure from high pressure, low volume, up to 0 pressure and maximum volume. And each time you measure it, before you do, just take the bottle and go, just give it a whirl. And that'll help unstick it. Right. And then measure pressure and look at the volume. Put your data down. And that's all the data that you're going to get. But if we have time, you can do it a couple of times. You know, we call that replicate experiment. Replicate your experiment. It may not be exactly the same numbers the second time. Then, how do you treat your data? So this is one where you're going to have a graph. So that's why at the very beginning we did that exercise in Excel. Because with Excel, you can graph your data. You can print it out, print out the graph, and cut it. And well, actually, you put it in your notebook, cut it out, paste it in your notebook. And remember, whenever you do that, paste it in your notebook, sign it across that edge. Right? That's to ensure that if something happens to it, you'll see part of your signature there and know, uh-oh, something's missing. You may not be able to recover it, but at least you know something went wrong. Okay, back to the graphing your data. When you graph your data, you should get something like that, a hyperbola, pressure against volume. So then you go and transform your volume values to inverse volume. So the units here would be milliliters, units here would be milliliters to the -1. Right? Because if milliliters here and you put them on the bottom, then overall, your units is milliliters to the -1. Right? And you'll have a data here, 1/V, corresponding to each of your total pressures. You don't plot this one, you plot that one. Total pressure. So when you do that, you should get a straight line. And you can do both of these in Excel. Now, drawing a smooth curve may be difficult in Excel, but do the best you can.
I know you can do like a curved line, like you can, like you draw like just a straight point, and then you can grab it in the middle, like pull where it
Okay.
I know you can't do that. I've done it before on there.
So what do you do with that for your report? Well, if you highlight it and print it to a file, like print it to an image file would be the best, like a JPEG or a GIF. then you can take, when you do your Word document, you can insert the GIF file, the image file in there. And you can move it around, situate it, put a title under it if you want. In fact, that'd be advisable.
The graph.
The graph itself. Yep. Okay. Any questions? You might think of some more when we get in there and start doing it next time. But that gives you something to think about, and hopefully preparedness is your best guarantor of safety. You know what you're doing when you go in, you're less likely to make a mistake. You go in there with a cold document and try to do the experiment just reading instructions, then you're just asking for trouble. And some students get it too. Wrong kind of trouble. Not just grade trouble, but like flying particles in your face, stuff like that. So know what you're doing before you go in. That's your safety guarantee. That plus wearing the right clothes. Cover up your toes, cover up your legs, bring your lab coat. Okay. And like I said before, you're going to have to wear eye protection for this one, especially since I know now that those bottles have a limited life. I mean, even new bottles could explode. So what you do is, when you get your pump going, you got the tube over to your, attached to your vessel, sitting over here, and you're over here pumping it, right? So if it blows up, at least you've got some distance between you. Because I heard when people responded to that last accident, man, it sounded like a gun went off. We were about to head for the door, So what's the FBI say when you hear gunshots? Run, hide, fight. That's their idea of how to deal with an active shooter. Run, hide, fight. Oh yeah.
I suggest the quiet method. Might as well stick it out and get the shot up anyways.
Well, yeah, that. Plus, I'd rather have a weapon. If I'm going to fight, I want equal. The equalizer. But the board of governors and the state legislature don't see it that way. They prefer soft targets. Ooh, I'm being recorded. I better cut that out before I publish it, right?